Molecular theory of viscosity of gases at low density. So consider a pure gas which is composed of rigid, non-attracting spherical molecules of diameter d, mass m and number density n. Number density means the number of molecules per unit volume. And it is considered that this number density n is very small such that the distance to be travelled by the molecules for exchange of momentum with another molecule is very high. That means the distance between the molecules is considered to be very much greater than the molecular diameter. So you have studied about the kinetic theory of gases, and from that can have certain equations. So from kinetic theory, the mean molecular velocity, that is u bar, its equation is root of 8 kt by 5m. So let us take this equation as equation number 1. Then the frequency of molecular bombardment per unit area on one side of any stationary surface exposed to the gas, that we are taking it as Z is equal to 1 by 4 n u bar. Then the average distance traveled by a molecule between successive collisions, it is called as the mean free path lambda. Equation for lambda is 1 by root 2 into 1 by pi d square n, that is equation number 3. So in order to determine the viscosity of this gas in terms of the molecular properties, the behavior of the gas when it flows parallel to the x-axis with a velocity gradient dvx by dy is considered. So here we have to assume that the gas molecules are moving in layers. So this is the first, this is a layer, this is another layer, and this is another layer. And we take the distance between two successive layers as small letter a. And we consider that, so we have seen the velocity profile when the upper plate is fixed and the lower plate is moving. So we got a velocity profile in the first class. So remember that also. And let us consider this layer. We assume that the velocity of this layer is vx of y. That means the velocity, it is varying along the x direction. So, and we know the molecules in these layers are moving in straight lines, and they changes their direction only when collision happens between any two successive molecules. So if any molecule reaches from this upper plane to this plane, we take its velocity as vx of y plus e. We are denoting a positive sign for this upper layer, and if any molecule reaches from this lower plane to this plane, we denote its velocity as vx of y minus a. And this is lambda, this distance between to the successive planes, that is the average distance between any two successive plates, is given by the kinetic theory as mean free path lambda. And also the molecules reaching a plane have on the average had their last collision at a distance a from the plane. So the equation for A from kinetic theory is 2 by 3 lambda. So we have 4 equations available, and we are making use of these 4 equations in order to get the viscosity of this gas. So the flux of x momentum across any plane of constant y is obtained by summing the x momenta of molecules that cross in the positive y direction and subtracting the x momenta of molecules that cross in the negative or the opposite direction. So this is the momentum flux tau yx. So its equation you can write as mass into Vx of y minus a into Z. That means this is the flux that is crossing in the positive y direction minus m into Vx of y plus a into Z. This is the flux that is crossing in the opposite direction. So we are putting in the minus sign here. So this is equation number 5. Then we can take this Vx of y minus a. We know an equation f of x plus a is equal to f of x plus a into f dash x by 1 factorial. So we can make use of this equation here. So this Vx of y minus a will be Vx of y minus a into dou Vx by dou y. So similarly, Vx of y plus a will be Vx of y plus a into dou Vx by dou y. And we have an equation a is equal to 2 by 3 lambda. So instead of a in these two equations, substitute 2 by 3 lambda. So Vx of y minus a is equal to Vx of y minus 2 by 3 lambda into dou Vx by dou y. That is equation number 6. Then Vx of y plus a is equal to Vx of y plus 2 by 3 lambda into dou Vx by dou y. That is equation number 7. Then substitute equation 6 and 7 in equation number 5. So you get dou yx is equal to mz into minus 4 by 3 lambda into dou vx by dou y. That is your equation number 8. And we have an equation for z, that is 1 by 4 n u bar from kinetic theory. So substitute the value of z and you get minus 1 by 3 into m u bar n lambda dou vx by dou y. That is your equation number 9. Then we can make use of Newton's law of viscosity. So you know equation for Newton's law of viscosity is dou yx is equal to minus mu into dvx by dy. That is your equation number 10. So you can compare these two equations, equations 9 and 10. So comparing, we get the expression for viscosity as 1 by 3 mn u bar lambda. That is equation number 11. Then substitute equations 1 and 3 in 11. Substitute for u bar and lambda. Then after substituting, we get the expression for mu as 2 by 3 into root of m k t by pi raised to 3 by 2 d square. This k is called as Boltzmann constant. So this expression for viscosity or this derivation is referred to as the rigid sphere model. This is called as the rigid sphere model. And this rigid sphere model, that is mu is equal to 2 by 3 into root of m kt by pi raised to 3 by 2 d square. So in this rigid sphere model, mu is independent of pressure. So the mu is independent of pressure agrees with experimental data up to 10 atmospheric pressure only at temperatures above the critical temperature. And also the predicted temperature dependency, that is mu directly proportional to root T. It is also less satisfactory. The data for various gases indicate that mu increases more rapidly than root T. So it is necessary to replace this rigid sphere model by another model that which includes the attractive and repulsive forces more accurately. In this rigid sphere model, we are not considering the attraction or repulsion between the molecules. We are not considering the intermolecular attraction. So owing to the disadvantages of this model, we have to consider another model which includes this attractive and repulsive forces more accurately, and it is also necessary to abandon the mean free path theories, and we have to use a Boltzmann equation to obtain the molecular velocity distribution. So we go for another model. So it is the Chapman-Enskog theory.